Electromagnetic waves. Electromagnetic waves, we tend to understand that the electric part of the wave is always running like a perpendicular to the electric field, which would go along this along an axis. So the absorption, now we'll just get onto the absorption in dielectrics. We consider a monochromatic plane wave represented by real parts of a pair of electric and magnetic fields, E and B here. If n omega is complex, then so is the wave number given here. Therefore, we go through a little bit of algebra and plug it in and multiplying out, and the real part gives the physical electric field here. And assuming KIMAJ, which means imaginary, is positive, this is a traveling plane wave that's exponentially dampened. It means decreased amplitude by a factor of the exponential negative K imaginary Z, which graphically is reducing here. And then now the Poynting vector, which is given here. The average Poynting vector, the time average Poynting vector, the transport of power by a monochromatic plane wave is the important special case. Consider the physical wave here and the magnetic wave, and we're using this from the magnetic intensity, which we got in the last video, and the energy flux density for this wave is given here. And we're using the fact that we're comparing the operation of unit vectors like the cross products, and we're getting EZ from this, and we're taking c squared to be 1 over epsilon naught mu naught, which is in free space, which gives this as a Poynting vector. The right hand side is positive, so n represents a net energy flow per unit area. It is often to know the time average of the flux density. The time average of cosine squared, k sub z minus omega t plus phi at any fixed position z is 1/2, because it's going to be 1/2 because if you picture an axis going along like this and a wave is cutting through the axis and going across like this, so the average of this wave is basically going to be the axis here. So the half, it's a half of, yeah, it's the half of this cosine squared. I don't know if I'm getting myself confused here. I think I'm in the right ballpark anyway. So for a value of z, the time average of the energy flux density n is given here. For a wave with propagation vector k and the electric field amplitude E naught, the time average Poynting vector in coordinate form is given here. Now electromagnetic wave equations in free space are given here, and Poisson's equation and Laplace's equation, which these are the ones that are used quite extensively in electromagnetism. Well, less so Poisson's equation, and in fact Laplace's equation. The main two are going to be the top, basically. These will be used the most. But yeah, I think I confused myself a little bit there with the average, time average. So the time average, so a cosine of 0 is 1, cosine of 1 is, yeah, I think it's maybe the sum of cosines divided half. I'm really getting confused about this, but I'll get back to you on this. I'll upload another video explaining this afterwards. But thank you very much anyway. Please do subscribe.